We're going to go ahead and jump into 7.2, an impulse. So we're looking at the fact that impulse is the product of the force that acts on an object and the time over which it acts. Impulse always results in a change in momentum. So we'll go into this a little bit more as we move on. Please ignore my very whiny cat in the background. So we are looking at two formulas, or one formula, the fact that impulse is equal to our force times our change in time, or a time interval. And we already know the fact that impulse causes a change in momentum, so we can sort of combine that force times delta t is equal to delta p. So we're going to pull all those ideas together. Right? Like I said, a force acting for some particular time does produce an impulse. An impulse is a change in momentum. We are looking at new units, technically speaking, but they're not any different than what we talked about before. So if we go ahead and take what we see here in the equation, we have force, we have time. When you take the two units that come with that, we get newtons and seconds. And when you multiply them together, you get newton seconds. Again, this doesn't boil down to a new unit. However, this is also equivalent to the unit we talked about last section, a kilogram meters per second. Let's go ahead and look at that. 1 newton is equal to 1 kilogram times meters per second squared, mass times acceleration. Right? Now we're taking newtons and multiplying it by seconds. So we're multiplying this term by seconds. I have seconds in the numerator. I have seconds squared in the denominator. So that cancels. That leaves us with the kilograms meters per second, which is exactly what we have here. All right? So these two units are equivalent, and you can use them interchangeably when you're talking about momentum or impulse. All right? So this can also be used as a unit for momentum. This can also be used as a unit for impulse. All right? Impulse is a vector, just like momentum is a vector. Impulse points in the direction of the force, just like momentum pointed in the direction of the velocity. All right? We're not always necessarily concerned with the directions themselves. We're more concerned with the magnitudes in many cases, but direction does matter sometimes because they are vectors, so we do need to keep them in mind. All right, so let's go ahead and look at our first example problem here. So we are going to push on a 22 kilogram shopping cart. All right, so we have a mass of 22 kilograms, and we're going to push with a force of 6.5 newtons, and we're going to push for a time interval of 1.6 seconds. What is the magnitude of our impulse that we're going to deliver to the cart? We just learned the fact that impulse is equal to the force times the time interval, right? So we don't actually need the mass here, but we're going to go ahead and use these other two pieces. So my impulse is equal to 6.5 newtons times 1.6 seconds, and we get an impulse of 10.4 newton seconds. All right. When you are putting things like this in mastering physics, it is important that you put the little multiplication sign between your units. Otherwise, it's going to think it's a compound unit and it's going to get confused. So, like I said, for mastering physics, it's going to be newtons times seconds. All right. So, well, I said before this mass wasn't relevant. We could use it to find more information here. If, for example, I said that we started from rest, we want to know what is the final velocity, we could do that. I'm not going to today, but we can come back to that as needed. Right? We are looking at the fact that impulse is a change in momentum, and that sort of ties back into that example problem I was talking about last time. We could use that and expand upon it to find that change in momentum based on other information in the problem. So let's do a different one. So we are going to look at the fact that some force acts on a bicycle for 12 seconds. So we have a time interval of 12 seconds. And it changes its momentum from, so this is our initial momentum, 15 kilograms meters per second in the positive x direction, so this is positive, to 38 kilograms meters per second in the positive x direction. So another positive 38 kilogram meters per second. We want to know the magnitude and direction of the force. Okay. So we're going to combine the change of momentum and the impulse idea that we looked at before. We saw that impulse was equal to F times T, which is equal to a change in momentum. Remember, that little triangle means change in. It means the final of a quantity minus the initial of a quantity. All right. As a result, I can rewrite this. I have F times T is equal to P final minus P initial. All right. We're solving for S, so I'm going to divide both sides by T. Right. Now my equation is solved for the variable that I want. I can go ahead and plug and chug. My final is at 38. My initial is 15. And I'm dividing this whole thing by 12 seconds. Hopefully you recognize the fact that we're taking kilograms meters per second in the top, and we're dividing that whole term by 12 seconds. So you should get the appropriate unit of Newton. So when I do that, plug everything in my calculator, I get a force of 1.916 repeating newtons. Right? We get 2 sig figs, so in this particular case, my force is going to be 1.9 newtons. So something to think about. We have a person standing under an umbrella during a rainstorm, holding an umbrella. After some time, the rain turns to hail. Though the number of drops hitting the umbrella remains the same, as does the relative mass and velocity of each, which case will require more force to hold the umbrella in place. So case 1 is rain. Case 2 is hail. All right. So in this particular case, my initial momentum in both cases is going to be negative. All right. However, in case 1, so my initial momentum is negative. In case 1 with the rain is hitting the umbrella and sort of coming to a stop. So my final momentum is 0. In case 2, again, my initial momentum is negative because it's moving downward. Initial momentum is negative because it's moving downward. But my final momentum is where we're going to see that change. We are seeing the fact that the hail is going to hit the umbrella and then bounce back up. All right? So that means my final momentum is actually going to be positive. So in both cases, we're going to go ahead and assume the time remains the same. Okay? So we're looking, so the force is going to be related to that relative change in momentum. So my change in momentum here, I'm going to go call this is negative P. This is 0. This is negative P. This is positive P. All right? So my change in momentum here is 0 minus negative P. So my change in momentum is just P. In this particular case, my change in momentum is a positive P minus negative P, that change in direction. And we get the fact that my change in momentum is 2P, right? So when something comes to a stop, it is a much smaller change in momentum than if something bounces. That is the one big takeaway here. If something comes to a stop, it is a smaller change in momentum than if something bounces. We're going to look at another example problem here. So we have 3 friends push a stalled car and its driver to a nearby service station. Assume there is no friction and the car is on a smooth, level road. that means that all of the force that the friends put in is going to actually translate to changing the momentum of the car. Right? So we are looking at the fact that the car is initially at rest, so VI equals 0. And the three students give a combined push of 305 newtons. So we have 305 newtons. We want to know the momentum of the car and driver after 12 seconds. So we got time of 12 seconds, and we want P final. All right. So we know the fact that impulse is equal to a change in momentum. All right. So the force times time, or our impulse, is equal to a change in momentum, or impulse is equal to F times T is equal to PF minus PI. So we're going to be focusing on this section of this equation. So F times T is equal to PF minus PI. We're looking for the initial, the final momentum. We have the force, we have the time. We don't have the initial momentum. However, if my initial speed is 0, think about what my initial momentum has to be. Right? If my initial speed is 0, right, looking at this equation, then my initial momentum is 0. So this term actually goes away. As a result, my final momentum is going to equal the force times the time. So we're going to go ahead and plug all that information in. So 305 newtons times 12 seconds. And we get a final momentum of 3,660 kilograms meters per second, or Newton seconds. Either is valid in terms of units. So this is part A. And we get 3 sig figs in both places. This is 3 sig figs, so we don't have to make any changes to this number. So part B asks if the mass of the car and driver is 1,300 kilograms, or 1,360 kilograms. So now we have a mass. We want to know the final velocity. Well, we're going to go back to this equation. We know that momentum is equal to mass times velocity, so my final momentum is equal to my mass times my final velocity. So a premise we sort of used before to get rid of that initial momentum here. So as a result, my final velocity is going to equal my momentum divided by my mass. We have our momentum, we have our mass. And as a result, we get 2.691176471, so on and so forth, meters per second. If we go ahead and adjust this to sig figs, I'm going to put this where we can see. And if we adjust this to sig figs, this is 2.69 meters per second. Right. So we are looking at the fact that time and force are inversely proportional. So if we look at impulse is equal to force times time, right? If we are keeping this the same, if this goes up, this has to go down, right? We could also rearrange this. If I move time to the other side, force is equal to impulse divided by time. This is a format you're more familiar with. So because this is up here and this is down here, as this increases, this will decrease, whereas this decreases, this will increase. So that's what we're looking at in terms of force and time. This is a big one when it comes to collisions, all right? If we are looking at a car, right, and it comes careening into a brick wall. This is actually why your car crumples in the front. What you're doing is it has to have the same change of momentum. It has to have the same impulse. It was going some particular speed and it's going to come to a stop. We can't change that particular fact. What we can do is make adjustments to how these are distributed. right? So the longer it takes for your car to actually come to a stop, right? So the larger we get this number, the smaller the force will be, right? That's how to minimize the actual damage to you in the car. If you get into an accident, you want to extend the time. So that's what airbags do. That's what the crumple zone on your car does. That's what helmets are supposed to do. They're supposed to maximize that time to minimize that force in a collision. And that is everything for 7.2. Have fun.